Okay, welcome everyone for this special physics/astro colloquium. We took the physics time and the astro location. Since you're here, I'm guessing you have heard the news. The NANOGrav collaboration, together with some international partners, put out a list of papers yesterday detailing the results, the latest results for the search for the stochastic gravitational wave background, the nanohertz regime. And today we have Pat Meyers to discuss the results. So Pat did his PhD in University of Minnesota, working on the stochastic background, but from the LIGO side, so the ground-based detection effort. Then he moved to Australia at UNIMEL for a postdoc to again work on the stochastic LIGO background and continuous waves from neutron stars, and joined Caltech about 2 years ago to work on NANOGrav. And as he's going to tell you, that was a great time to be joining NANOGrav and switching from LIGO stochastic background to NANOGrav stochastic background, because he's about to tell you some first results towards the effort to find this background. So without further ado, we should get started. Take it away.
All right, yeah, thanks, Katerina. So I'm excited to be here today to talk to everyone about NANOGrav's evidence for a gravitational wave background. And of course, it's not just NANOGrav today. This is an international effort, including other pulsar timing arrays as well. But as a NANOGrav member, I'm going to be telling you mostly about the NANOGrav results. So I joined at just the right time, about 1.5 years or 2 years ago. Yeah, so let's go ahead and jump right into it. It's not working. Okay. There we go. Okay, so this is our signal. This is the spectrum of the gravitational wave background that we have evidence for. So on the y-axis is the amplitude, and on the x-axis is the frequency. And this is something that we had evidence for in the 12.5-year data set, but the new thing here is this evidence for correlations. So if you have pulsars separated on the sky by some angle, their signal should be correlated with some predicted correlation pattern, and the blue represents our data, while the black represents the prediction. So hopefully by the end of this talk, you'll understand what all of the intricacies of these slides are. So let's put this in the greater context of the gravitational wave spectrum. So on the far side, we've got things like ground-based detectors like LIGO and Virgo, which most notably detect binary mergers of compact objects. In the middle, we've got space-based detector LISA, which will hopefully fly in the 2030s, is going to see hopefully like millions of sources. As you move down into the years-long regime for your gravitational periods, we're talking about supermassive black holes. So these are the massive black holes at the centers of galaxies. Those galaxies merge, and those supermassive black holes end up in binaries with one another, and those binaries emit gravitational waves. And that's the signal that we're interested in with pulsar timing arrays, and that I'm here to talk about. There are also other potential sources at these lower frequencies, things like cosmic strings, things like gravitational waves produced in the early universe. You can probe those things using cosmic microwave background, for example, so you can look at the imprint of gravitational waves on the polarization of the cosmic microwave background as well. But today, we're talking about this roughly 15-year gravitational wave period, and that's in contrast to the binary black hole mergers that LIGO saw, which are on the order of tens to hundreds of hertz. So this is quite a long effort of observation. So NANOGrav itself is a roughly 200-member, 70-institution interdisciplinary collaboration. It includes expertise from radio astronomers to neutron star astrophysicists and gravitational wave scientists. It was created in 2007, and it's been funded as an NSF Physics Frontier Center since 2015. Our observations in this data set were made by the Green Bank Telescope, the Arecibo Telescope, and VLA, and then hopefully, not hopefully, in our next data set, we'll have data from CHIME as well. We are one member of the International Pulsar Timing Array as well. So we've got NANOGrav based in North America, the European Pulsar Timing Array, or the EPTA, based in Europe, the Parkes Pulsar Timing Array, which uses the Parkes telescope in Australia, They're sort of the three founding members. Recently, the Meerkat PTA and the India PTA have also joined, and the Chinese PTA has been timing pulsars for the last few years as well. So there are results from everyone on here except Meerkat today, which is pretty exciting. These are the members of the JPL and Caltech team who work on NANOGrav. Here, so Sophie Howrahan, who's a graduate student, Aaron Johnson, who's another postdoc, Katerina, who is a professor here at Caltech, and then Kurt, Joe, and Michele, who are senior scientists at JPL. And then there are other NANOGrav members here, down here in the corner as well. And there are some former members of the group, all of whom, except for one, are still working on pulsar timing arrays, which is pretty exciting. And sort of the greatest hits from this group involve working on formulating statistics for how to make a detection of a gravitational wave background, writing and reviewing the code used to do those searches, and leading the paper writing effort and the search effort for this search that's been done on past data sets. So today, NANOGrav has 8 papers that you can read this minute. 4 of them have been published in AppJL. 2 of them have been accepted to AppJL, and 2 of them are on archive. So the blue stars represent papers published in AppJL. The pink are the ones that have been accepted, and the 2 at the bottom here are on archive, and you can read them now. And this QR code takes you to a link that has all 4 of these papers with blue stars that you can read. And the 3 big ones that we're really highlighting here are the dataset paper, so the paper that describes the dataset and the timing of these 68 millisecond pulsars, the detector characterization and noise budget paper, so this discusses a lot of the noise models that are used, and the paper that presents evidence for a gravitational wave background. The IPTA has several members, and a lot of people have put out papers today, so I want to highlight that work. So NANOGrav, as I said, timed 68 pulsars. We have 16 years of data, and we have roughly 4 sigma significance for correlations if you use a frequentist optimal statistic, and roughly 3 sigma significance if you use a fully Bayesian statistic. The Parkes Pulsar Timing Array has timed 32 pulsars for 18 years, and they have roughly 2 sigma significance for correlations. They present some concerns about their systematics as well, but you can see their correlations over here on the right look Hellings and Downs-like. The EPTA and the Indian Pulsar Timing Array have combined their data sets. They have 25 pulsars that they've timed for 24 years. 10 of those years are on modern, very sensitive instruments, and so they present sort of 2 slices of their data set, one of which that uses the full 24 years, one of which that uses the 10 years, and they present, again, roughly 3 sigma significance using their best data, that data from the last 10 years, and you can see those correlations on the right. And the Chinese Pulsar Timing Array has timed 57 pulsars for 3.5 years. They report 4.6 sigma significance. Their significance is in a single frequency bin because they've only been observing for 3.5 years, and you can see their correlations down here as well. And it's important to note that direct comparisons between these data sets are ongoing, and hopefully results will come out quite soon on direct comparisons, and then an actual data combination effort for the first three groups on here is underway. And so hopefully we'll have sort of a super data set that combines everyone's data set pretty soon. So I want to back up and I want to talk about what gravitational waves are. What is the signal that we're actually looking for? So if we start with the space-time metric, we have the metric that's used to calculate the proper distance between events in space-time. We can expand this in terms of the Minkowski metric plus some small perturbation. And if we put this into Einstein's equations and we only keep things to linear order in that perturbation, we find that those perturbations satisfy a wave equation. So great, they're waves. What do they actually do when they pass by us? So these things propagate at the speed of light, which means that their effect is transverse to their direction of propagation. So if you have a gravitational wave propagating into the screen here, and you have a ring of test masses, then that ring of test masses, as you move through time, will get squeezed in one direction, elongated in another, return to its original form, and then it'll do the same thing in the perpendicular direction. The gravitational wave amplitude itself is measured in strain, so the change in length divided by the original unstretched length. So in this case, that would be the blue arrows that you see there divided by the original length of the ring. And this strain is the fundamental thing about gravitational waves. So if you imagine a gravitational wave of the same size, but a larger ring, then those blue arrows will be correspondingly larger. So this is why gravitational wave detectors like to be very, very big. There are two polarizations that we talk about, a plus polarization and a cross polarization that are 45-degree rotations of each other. Since gravitational waves propagate at the speed of light, we've only got two polarizations similar to electromagnetic radiation. So we should talk about what the typical gravitational wave amplitude is that you might expect. So we've got an expression for the strain of the gravitational wave here, and it's going to fall off as 1 over the distance to the source of the gravitational waves. We have some fundamental constants here that are quite small. And then we have the second time derivative of the quadrupole moment. So the quadrupole moment in this case is going to be proportional to something related to the mass scale of the system that we're looking at, multiplied by some length scale of that system squared. And so what that means is that you need very massive things moving very quickly to produce meaningful strains from your gravitational waves. So on the right is a pictorial example of one of these things. This is a supermassive black hole binary. So the strain roughly for a binary, like what you see there, goes as something like the mass of the system to the 5/3 times the frequency of the system to the 2/3 divided by the distance to the source. And if we're talking about very heavy masses, we're usually talking about lower frequencies. If we're talking about lighter masses, we're typically talking about higher frequencies. So if you think about LIGO, whose black holes are on the order of 30 solar masses and whose frequencies are of order 100 hertz, and then you move to this pulsar timing array band where you've got 10 to the minus 9 hertz, we're talking about like 10 to the 9 solar masses for the black holes. So if we plug in rough numbers into this expression here, for LIGO merging black holes, we've got masses on the order of 100 solar masses, frequencies on the order of 100 hertz, and a strain on the order of 10 to the minus 21 if we put this at 400 megaparsecs. If we're talking about these in-spiraling supermassive black holes, then we're talking about masses on the order of 10 to the 9 solar masses, so significantly larger. Frequencies on the order of 10 to the minus 9 hertz. That corresponds to a 30-year period for the gravitational wave. And if you put it at the same distance to the source, 400 megaparsecs, then you get out a significantly larger strain on the order of 10 to the minus 17. Okay, so I've talked about gravitational waves, what their typical strain amplitudes are. Let's talk about how people detect them. So LIGO is a little bit more intuitive than pulsar timing arrays, so I'm going to start with detectors like LIGO and Virgo first. And if you have merging black holes here, you have gravitational waves propagating away from them. We're talking about of order 100 hertz, and you've got wavelengths on the order of 3,000 kilometers. The way that LIGO and Virgo make detections is they send in a laser. That laser gets split in 2 perpendicular directions, and you measure the path length of that laser in those 2 perpendicular directions. So when the lasers come back and they recombine, and you measure their interference pattern at this output source, then typically the detector is set up such that these things destructively interfere if there's no gravitational wave. But if a gravitational wave passes, then the path length traveled by this laser is a little bit longer in one direction than it is in the other. And so you get some different interference pattern out, and you get some extra pattern of light here that encodes the information about the gravitational wave. So this is the way that LIGO works, but we're using pulsars and pulses from those pulsars instead of lasers and mirrors to try to make a detection. So pulsars themselves are rotating neutron stars. Neutron stars are sort of the end of life scenario for some of the most massive stars in the universe. And these neutron stars have very high magnetic fields, and they're rotating very quickly, meaning that they're emitting quite a bit of radiation out of their poles. And depending upon the geometry, that radiation can sweep through us like a lighthouse. And every time that this pulsar rotates, we'll get some amount of radio emission that we can see. And so each time we get a rotation, we get some pulse. And the shape of this pulse is what we call the pulse profile. For the best timed pulsars, the rotation frequency of these pulsars are very, very stable. And you can predict when the next pulse will arrive to of order tens of nanoseconds. So they're very predictable objects. They're very stable clocks. So on very long timescales, they act like clocks that are on the order of sensitivity of like atomic clocks. Pulsars themselves were originally discovered by Jocelyn Bell Burnell and Anthony Hewish in 1967. And millisecond pulsars, which are the ones that we're using to search for gravitational waves, were discovered in 1982 by Bakker et al. So, you know, pulsars are themselves very interesting outside of just searching for gravitational waves using pulsar timing arrays. So I think a lot of people are familiar with the Hulse-Taylor binary. It was discovered in 1974, and Hulse and Taylor were awarded the Nobel Prize for it for the discovery of the system in 1993. And the hardening of this orbit, the decay of the orbital period that you see is consistent with that binary emitting gravitational waves. You can also use pulsars, you can also use pulsar timing to try to measure the mass of neutron stars. So in this case, if the neutron star is in a binary and that binary is edge on, the Shapiro delay of the pulse as it passes by a companion can be used to measure the mass of the companion and the mass of the neutron star. And this is how a lot of the heaviest neutron stars have been measured. So I mentioned that we can predict when these pulses arrive to very good accuracy. So let's talk about that actual physical model that ends up being built. So we have some time that this pulse arrives in our detectors, and we need to correct for lots of physical processes before we actually look for gravitational waves. So we want to correct for any errors in the clocks at individual sites. We want to correct for any errors in the atmosphere that we can measure. We want to reference everything to the solar system barycenter, and so we need to know to great accuracy where on the sky these pulsars occur. So this would be the Romer delay as the pulse travels across the solar system. The Shapiro delay due to heavy objects in the solar system. The dispersion measure, which essentially says that that pulses at higher frequencies will arrive, the piece of the pulse from higher radio frequencies will arrive sooner than the pulse at lower frequencies. And so this is something that we have to both measure and model. And I'm not going to talk in detail about the models of the dispersion measure, but if people have questions, I'm happy to try to take them. We have to correct we have to physically model the binary properties of this pulsar if it's in a binary with some companion. And if that binary is losing energy due to gravitational waves, we also have to account for this. So this is all stuff that's happening sort of in between us and the pulsar, but the pulsar itself, we want to model its rotation. And so we typically model its rotation using a Taylor expansion in the orbital phase. So we have some initial phase, we have some frequency of the rotation, and some frequency derivative of that rotation. So over here on the right, if we're predicting when pulses arrive and we get one of these pieces wrong, say the Romer delay, let's say we get the position, the declination of the pulsar wrong on the sky, then we'll have errors in our prediction for when the pulses arrive that look sinusoidal with a period of roughly a year. If we're getting the frequency of the rotation wrong, then we're just going to see a linear offset in how badly we're predicting these arrivals. Same thing, we get a quadratic offset if we're talking about the frequency derivative. So those are all the things we try to physically model, or some large subset of the things that we try to physically model. And then we have something that's left over here that's called Y-res. And in here would lie effect due to gravitational waves, effect due to intrinsic red noise of the pulsar. So pulsars are neutron stars, and there's a lot of interesting internal physics going on in these neutron stars that's not particularly well understood. But one thing that almost all pulsars exhibit is some stochastic wandering of this rotation frequency as a function of time. And that stochastic wandering can look like gravitational waves if you're looking at an individual pulsar. This is why we observe many pulsars, because the effect of gravitational waves should be present in all of the pulsars that we're observing, whereas this noise due to the internal physics in that neutron star is going to be intrinsic to that individual neutron star. And then we have white noise due to, say, noise in our detectors. So down here, on the y-axis here would be this Y-res that we talked about right here. And this is for one of our best timed pulsars, J1909 minus 3744. And you can see that we've got some wandering here, some stochastic wandering. And what's interesting about this pulsar is that this wandering here is completely attributable to that signal that I showed on the second slide. So a lot of pulsars will have some intrinsic red noise, but this particular pulsar, all of this stochastic wandering here is attributable to this gravitational wave background signal that we have evidence for. Okay, so I've talked about individual pulsars. Let's upgrade this to a pulsar timing array. So now the arms of our detectors are the pulsar Earth system. The gravitational wavelength that we're talking about here is of order a parsec if we're talking about frequencies on the order of 10 to the minus 8, 10 to the minus 9. And the distance from the Earth to the pulsar is of order a kiloparsec in general. And so this actually brings up a distinction compared to when you're thinking about, say, LIGO and Virgo, because for those instruments, the wavelength of the gravitational wave is much longer than the size of the detectors. And in this case, we have the reverse. The wavelength of the gravitational wave is much smaller than the distance to the detectors. And this actually means that the intuition that we built for LIGO is close, but not quite right. And I'll talk in the next slide a little bit more about that. But we end up observing many pulsars, as I said, 68 for NANOGrav, and we look for a common gravitational wave signal in them. So the intrinsic red noise would be for an individual pulsar, but the gravitational wave piece should be correlated across lots of pulsars. So I want to spend a lot of time on this slide to give you an idea of how a gravitational wave will affect the arrival of pulses from an individual pulsar. So we've got a schematic here. We've got a pulsar in the top right. We've got our radio dish down here. The gray lines, hopefully you can see them, correspond to wavefronts for our gravitational wave. We've got some vector pointing from the pulsar to the dish that we call p hat, and we've got some vector corresponding to the propagation direction of this gravitational wave, which we call k hat. And we're going to describe the wave field of perturbations using this HAB here. So if we have some time at which we see a pulse, some observation time, t-obs, this is going to look like, this is going to be related to the time that pulse was emitted, plus the distance between the Earth and the pulsar, plus some extra piece due to the gravitational wave. So in this case, we've got the line of sight contracted with the gravitational wave field, and we're integrating from the time that this pulse was emitted up through the time that this pulse is observed. So we're integrating from when the pulse is emitted, and we're integrating the effect of the gravitational wave all the way until it's observed by the radio telescope. So what this results in is a fractional change in the observed rotation period of the pulsar, which is labeled as p. So if you're clicking off pulses and you're looking for how long it takes in between them to measure some rotation period of the pulsar, then these gravitational waves will give you some fractional change in the rotation period of this pulsar. And that fractional change is related to the strain at the Earth and the strain at the pulsar when the pulse was emitted. And then we've got some extra response term out here, and we've picked up this dot product in the denominator that's related to how k and our line of sight are related to one another. And this may seem counterintuitive at first. We've done this integral from when it was emitted until when it arrives, and we find that in the end, all it depends on is what's happening near us and what was happening near the pulsar. But some intuition you can gain from this is if you think about the fact that these two pulses that allow us to measure a rotation period are emitted very close to one another. And so in that sense, the only piece of the gravitational wave field that's different that those two pulses will see will be wavefronts that enter and leave near the pulsar at the time it was emitted, and wavefronts that enter and leave this system at the radio telescope near the time that it was received. And so in the end, what we find is that this fractional change in the rotation period that you might observe is really just related to what's going on near the Earth and what's going on near the pulsar. So these are what are often called the Earth term and the pulsar term. So you can integrate this fractional period to tell you what the actual delay is due to the gravitational wave field that this pulse is seeing. And so if we're integrating this thing over time, and this delta p over p is proportional to h, then what you find is that this delta t is proportional to h divided by the frequency of the gravitational wave squared. So delta t is proportional to the amplitude, the strain amplitude of the gravitational wave divided by the frequency of the wave that we're looking at. Okay, so what sort of signal might we expect to see? So one of the most promising potential sources are superposition of many unresolved supermassive black hole binaries. So the signal from these would be dominated by the in-spiral of these systems, and a single source would be roughly monochromatic. And you might say, well, do you have to worry about the merger of these systems? No, the systems that we're sensitive to are going to merge out of our frequency band. If you wanted black holes merging in the frequency band that we're looking at, which is roughly between 1/15 years and a year, or 1 over a year, then you need massive black holes on the order of like 10 to the 12 solar masses merging. And that's not something that's going to happen very often, if at all. If you have sort of an idealized system of these, or some idealized model for how these systems evolve, say if these binaries are getting closer to one another only due to gravitational wave emission, then what you find is you expect a power spectrum in those timing residuals, so that delta T GW, that follows a power law with some spectral index that goes as -13/3. So this is idealized astrophysics that gives you this prediction, and real things that happen will push you away from this 13/3. And a detection of this background of supermassive black hole binaries could tell us about the dynamical environment in which these supermassive black holes would form. And there's going to be more on astrophysics to come. But I just want to highlight that, one could potentially see an individual source, but what we have evidence for today is a superposition potentially of many of these sources. And there are other models that could potentially predict the signal that I'm talking about today. So if we're talking about a background of unresolved supermassive black holes, then we're going to make some simplifying assumptions. Okay, we're going to assume that this background is isotropic, so no preferred direction on the sky. And this might break down if our signal is dominated by some small number of supermassive black hole binaries. But if we assume that the signal is dominated by a large number, then probably it doesn't matter what direction we look in. We're going to assume that this signal is stationary, which for us means that it can be described statistically with a power spectral density. And then the last thing we're going to assume is that it's unpolarized. So an individual system will emit gravitational waves that are polarized depending upon the orientation of that system. But if we're adding up incoherently, lots of systems added together, those systems know nothing about each other, they're going to be oriented randomly. We're not going to have any polarization of the background. So if we take the delay due to gravitational waves that one pulsar observes, and we cross-correlate it with the delay due to gravitational waves that another pulsar observes, what we find is that this cross-correlation is going to be proportional to the power spectrum of the gravitational wave background divided by f squared. That's the 1 over f that I just talked about a couple slides ago. And then multiplied by this factor here that you'll notice doesn't actually depend on any properties of the gravitational waves. So this f is a response. So this is that response that we saw again from a few slides ago. What we have is the product of the response of pulsar I to a gravitational wave in direction omega hat, multiplied by the response of pulsar J to a wave in direction omega hat. And when you integrate over the sky, you get out some prefactor here that only depends upon the angle between these pulsars on the sky. And this is what the Hellings and Downs curve is. So in the end, this cross correlation here is proportional to this f to the -13/3 if we're talking about supermassive black hole binaries for our signal, multiplied by some like correlation coefficient. So if pulsar I and pulsar J are separated by say 60 degrees, then the gravitational wave pieces, if we cross correlate them for these two pulsars, are going to be, we're going to see something that looks like the spectrum of gravitational waves, but modulated by some correlation coefficient. Okay, so these next several slides are going to detail sort of how we do our analyses, and they're going to give us sort of pictorial examples of how we do our analyses. And these slides are from Sophie Harahan, who's a graduate student who's worked on NANOGrav. So we're going to build up a per pulsar noise budget. So I mentioned the per pulsar intrinsic red noise. So this is red noise that is individual to that pulsar. And then if we have some gravitational wave background, then that's going to have some spectrum here. And it might be less than this red noise. It might be a little bit bigger. We'll see in a moment that, it depends upon the pulsar that you're looking at. And then we have some white noise that represents our limit from our detectors, for example. So in general, we model both this per pulsar red noise and this gravitational wave spectrum as power laws. So that detector characterization paper that I mentioned at the beginning goes into a lot of detail trying to tell whether or not this assumption for the per pulsar red noise of a power law is good. What we find is that it works well. We have no evidence that the red noise in individual pulsars is deviating from a power law. So if you imagine just looking at the data from an individual pulsar, we're not going to be able to tell the difference between this red curve and this blue curve. We're going to see some combination of these things. But if we have several pulsars with a different red spectrum in each of these things, then even if we don't correlate our data, we're going to build up evidence that we have some extra piece here that is common. And so this is what we often talk about when we talk about searching for a common process. But that common process, as I said, should be correlated. And the correlations are going to depend upon the separation angle between those pulsars in the sky. And again, this is what we call the Hellings and Downs curve. So if you imagine building up a covariance matrix that says what happens if we cross-correlate data from one pulsar with data from another pulsar, then what we say is along the diagonals, we're going to have information about the red noise, the gravitational wave background, the white noise. But if we move off the diagonals, the only things that are going to be correlated are going to be the gravitational wave piece. And so what we really want to do if we want to measure correlations is we want evidence that these off diagonals here are non-zero. If you think about, say, pulsar 2 and pulsar 3, if they're quite close on the sky, then their correlation coefficient here is going to be quite close, say 0.5 if they're in the same direction, but they're two different pulsars. And if you have two pulsars that are separated by roughly 50 degrees on the sky, then you're actually going to see no correlation at all. So in the end, if our goal here is to say, okay, we want to measure correlations between our pulsars because that's really the characteristic of the gravitational waves that we're searching for, then what we do is we compare a model that includes these Hellings and Downs correlations to a model that includes no Hellings and Downs correlations, but does include the intrinsic red noise and a common spectrum. So over here, we have that common spectrum, that blue that's in all of the pulsars, but we're assuming that it's not correlated. And over here, we're accounting for those correlations. And what we want to do is we want to compare these two models, and hopefully this model on the right is preferred if we have evidence for gravitational waves. So the way that we do this is we calculate a Bayes factor between these two different models, modeling quite a few parameters in our data, and then we use this Bayes factor as a detection statistic. So before I move on to the actual results, I want to have a very brief note on noise models. So as I said, the per pulsar intrinsic red noise is modeled with the power law spectrum. So in a fully Bayesian analysis, that adds two parameters, the amplitude and the spectral index of that power spectrum for every pulsar that we have. And then on top of that, you have the amplitude and the spectral index for the gravitational wave background that you're searching for. So we're doing a Bayesian analysis with 67 times 2 plus 2 parameters. So it's a very large space that we have to explore using Markov chain Monte Carlo. The white noise is modeled as a mix of radiometer noise with some phenomenological rescaling that's been standard in the pulsar timing community for a very long time. And the dispersion measure fluctuations that we talk about are measured regularly and modeled in two different ways. And I'm happy to try to answer questions about that, but I'm not going to spend much more time on this slide. So the NANOGrav 15-year data set is what we're interested in talking about today. So up here, we have the different pulsars on the sky. The ones that VLA observes are marked with X's, Arecibo with the blue points, and GBT with the red circles. We have 16 years of data and 68 pulsars that we've observed for greater than 2 years. Since one of the things that we're interested in is the angular separation between pulsars, if we look at the distribution of how different pairs of pulsars are distributed as a function of angular separation, we see that we get pretty good sky coverage in terms of these angular separations. Maybe we would like a few more that are separated by 180 degrees. But for the most part, we're getting quite a few pairs of pulsars across here. We've got Arecibo here, Greenbank, and VLA, which made the measurements that go into the 15-year data set. In the future, we'll include CHIME data, and hopefully in the future, we'll also have DSA 2000 as well. So this is a nice pictorial example that can show sort of how NANOGrav's data set has evolved over the years. So each point on here represents an observation. Each vertical line represents an individual pulsar. And as you move from the top to the bottom, you're adding data to your array. So on the top, all of these points represent what's in the 5-year data set. And then we have the 9-year, 11-year, 12.5-year data set, and then all of the points on here correspond to the 15-year data set. The different colors correspond to different telescopes and different radio frequency observations. And a big thank you to Thankful Cromarty for this slide. So past results based on the 12.5-year data set indicated that we had strong evidence for a common process. So evidence that we have this extra gravitational wave background piece on our diagonals, but no evidence for correlations on the off diagonals. And the strength of the evidence for this extra spectrum that's common to all of the pulsars had a base factor of roughly 10,000. That base factor is now significantly larger in the new data set. But as I said, there was no evidence of correlations between pulsars, and really to say that we're seeing evidence for gravitational waves, we need to see these correlations. And IPTA colleagues saw a similar common process, but no correlations as well. But it's expected that this is how things would go. It's expected that we would see autocorrelations first, and then we would see cross correlations afterwards. And that's the way that things have gone so far. So this is the result. So hopefully now this plot makes a little bit more sense. On the y-axis, we have the correlation coefficient. On the x-axis, we have the separation between pulsars. And now our data are in blue. So the way that this data is generated is we cross-correlate two pulsars on the sky. And then we bin things up in terms of angles. So if we have 67 pulsars that go into our analysis, then we get 2,200 pairs of pulsars that can be used to fill out this plot here. Okay, and what we see is that we have 3 to 4 sigma significance for correlations. And on top of that, those correlations are consistent with the prediction from the Hellings and Downs curve. And you can actually test that consistency using a chi-square test, and we find that these things are in agreement with each other. So we have evidence of correlations, and those correlations are consistent with a gravitational wave background. So if we want to assess significance of our correlations, I said 3 to 4 sigma, and you want to have some idea of how we come up with those numbers. We have 4 different ways of doing this. I'm going to talk a little bit about the first one. So we apply random phase shifts to the data. We can't do something like what a lot of ground-based detectors do because our signal is on all the time, right? So we can't just look at a time where we have no signal and say, oh, that's what our noise looks like, right? We have to find some way to break our correlations between pulsars and then measure how frequently we might accidentally detect correlations when there are none in the data. And that's really what we're trying to do here. So we do this by introducing phase shifts to all of our pulsars, and then we perform our search either with this base factor or using a frequentist optimal statistic. We repeat this, say, 400,000 times. That's how many times we did this for the optimal statistic. For the base factors, I think it was 10,000. And this builds some null distribution for our detection statistic. And so this says, how frequently, if we didn't have correlations, would we accidentally measure correlations at some level? We have, as I said, we have 3 other ways of doing this, but I've focused on these phase shifts, as we call them. So these are our significances. So we've got, for base factors, we've got roughly 3 sigma significance. So we've got a base factor of about 200. And for our frequentist optimal statistic, we've got between 3.5 and 4 sigma, depending on how you estimate this background distribution. We've also got our spectral properties. So I said that we typically model these things as a power law. So we've got the amplitude of that power law referenced at 1 over a year. So this is the amplitude at some reference frequency. And the reference frequency we typically use is either 1 over a year or 1 over 10 years. And we've got this 13/3 line here. And that's what we talked about before for sort of an idealized population of supermassive black hole binaries. On the right here, we've got our spectrum as a function of frequency. So these blue lines represent sort of the uncertainty in this blue over here. And these gray violins represent what happens if you model each frequency independently. And you see that these gray violins agree pretty well with the power law. The difference between the blue and the red here is something you might be asking, and those differ on how we do our noise modeling. So this differs on how we model the dispersion measure fluctuations that these pulses see as they move between the pulsar and us. So let's move on to talking about our interpretation of this signal. So this is a slide from Luke Kelly, so a big thanks to him. So this spectrum is going to be dominated probably by an ensemble of massive black hole binaries in the universe. So things of order 10 to the 9 solar masses. in near equal mass binaries and at pretty moderate redshifts. And what happens in this spectrum encodes in it different physics. So if the spectrum, for example, goes from being steeper and then it turns over at low frequencies, where that turnover happens and how strongly it turns over will tell us about, say, stellar and gas interactions in that supermassive black hole binary. The overall scaling of this thing will tell us about the number density of supermassive black hole binaries in the universe and about the different masses that we're sensitive to. And then at higher frequencies, how this spectrum deviates, say, from our typical 13/3 will tell us potentially something about the distribution of eccentricities of these binary orbits and the distribution in redshift of the binaries that we're actually seeing. So what astrophysics can we actually constrain? So in general, we prefer higher masses per co-moving volume and shorter binary lifetimes. And the binary lifetimes in this case mean from when these things become gravitationally bound until they're emitting in our band. So on the x-axis here, we have mass, and on the y-axis, we have density of these binaries per co-moving volume. And the sort of grayish blue bands here represent priors, so you can see here, and the red represent posteriors. And so what you can see is that we're pushed up towards the high mass end of our posteriors. So we're seeing probably that the signal is dominated by higher mass signals than you might otherwise expect. And we're really only constraining things at redshifts of order 0.25 and 0.5. And out at higher redshifts, we're not constraining much. Up here, we've got the Bayesian prior that we put on the binary lifetime, and you can see that our posteriors are preferring shorter binary lifetimes. So this is a complicated and kind of pretty looking plot that hopefully I can walk you through. So color represents the frequency of the gravitational waves that we're observing. The y-axis over here corresponds to the solid curves, and that's the fraction of the gravitational wave background that is contributed by, say, masses at 10 to the 9 solar masses. These dashed curves correspond to the y-axis over here, which represents the number of binaries that are contributing. So what you can see is that lower frequencies are going to be dominated by higher masses. Higher frequencies, which would be the purple here, are dominated by lower masses. And what you can also see is that the numbers of these binaries, we've got many more that are probably emitting at low frequencies and fewer that are emitting at higher frequencies. You can also ask, how consistent is this signal with the literature? So there have been a lot of theoretical predictions over the years for how strong this background should be. What we find is that this is on the higher end of what a lot of those theoretical predictions made, but that in general, the signal is consistent with quite a few of the theoretical predictions that people have made over the years. There's also a very large paper searching for new physics. So you can consider cosmological interpretations of this signal. And we have no way of distinguishing between, say, some of these cosmological models and supermassive black hole binaries in this data set. Hopefully in the future, we will. They consider quite a few different models. So inflationary models, scalar-induced gravitational waves in the early universe, first-order phase transitions in the early universe, and topological defects like cosmic strings and domain walls. They find that stable strings from field theory can't reproduce the signal, but for the most part, all of the other models that they consider could reproduce this signal. But there's no evidence of new physics because the signal fits pretty much just as well as supermassive black hole binaries for all of these different models. They also search for ultralight dark matter, and they find no evidence of ultralight dark matter, but some of the constraints on those masses outperform other experiments. Over here is an example of the spectrum and sort of the full landscape across the frequency band. So the frequencies now down here span many decades, and we've got LIGO up here. So these were the limits set by LIGO in 2003. And we've got our spectrum over here with different models. So inflationary models on top, topological defects on bottom, and you can see that a lot of these lines agree with our spectrum, and then they make other predictions for what happens outside of our frequency band. You can also search for gravitational waves from individual supermassive black holes, individual supermassive black hole binaries, sorry. And so realistic simulations for these supermassive black hole binaries give maybe a 6% chance that a single source would have been detected in the 15-year data, and roughly a 41% chance at 20 years. So this is a nice paper by Bensei Beichi. And individual supermassive black hole binaries will emit at roughly a constant frequency. And so you're looking for roughly monochromatic signals, and you're doing it over a pretty wide frequency band and across the whole sky. So they search over this broad frequency band and they search over the whole sky. They find no detection was made, but they do find sort of an interesting blip down here that, depending on how you model the background, goes away. And what's interesting is that the EPTA also sees something similar in their search for continuous waves as well. Over here, you can set limits on the luminosity distance for a supermassive black hole binary of a certain mass at a specific frequency. And what you can see is that you're more sensitive where you have lots and lots of pulsars and less sensitive where you have fewer pulsars. And this really says, if we want to make a detection of these things, then we want pulsars all throughout the sky. And so, we want to start trying to fill out other places on the sky with our pulsars. So adding more pulsars to our array becomes more and more important. You can also perform a search for sort of generic anisotropies on the sky of this background. So at the moment, our evidence is for an isotropic background. There's no evidence of anisotropies on the sky, but it is very plausible that you might expect anisotropies, because if the signal is dominated by a limited number of supermassive black hole binaries, then you're probably going to be seeing hotspots on the sky corresponding to small numbers of supermassive black hole binaries. So no evidence of anisotropy was found, and so upper limits were set on the level of anisotropy in each direction. But there's some hope that this might be detectable with, say, 20 years of data. And there's a nice paper by Nihan Pol that goes through this and sort of forecasting when you might expect a detection of anisotropies. So I'm going to end by talking about looking towards the future, right? So if we could detect a turnover in the spectrum at low frequencies, this would unveil sort of information about environmental effects around these supermassive black hole binaries. So that would be very exciting. Distinguishing between supermassive black hole binaries and other potential models, for example, those cosmological models, would be really interesting. And one of the great hopes for something like that would be if you detect some sort of anisotropy, that means that the signal is almost certainly coming from supermassive black hole binaries, because most of these cosmological models, if not all of them, predict an isotropic background. And an individual supermassive black hole detection could come with an electromagnetic counterpart, and that would offer fantastic multi-messenger science. And then, as I said, there's a lot of science on populations of supermassive black hole binaries that you could potentially get as we get better estimates of the spectrum, as we start to measure how the spectrum deviates from 13/3, potentially how individual frequency bins are larger or smaller than others will start to tell us sort of about how these supermassive black hole binaries look in the whole universe. So I'm going to end there by leaving this plot up, and I'll go ahead and take questions.
Thanks, Matt. Before we start with questions, a quick note. After the talk, we have wine and cheese in the back patio, and also Hellings Down's cookie, so join us for this. A cookie with this, basically, courtesy of Sophie. Okay, and now let's start with questions. Start with the room. All right, I'm gonna get you the mic over there. I saw 2 hands, and now I don't know where they were. Let's start.
Great talk. Can you speculate on the origin of the larger than expected signal from FAST? And if it persists and if it's real, what does that mean astrophysically?
Yeah, so I wouldn't say that it's larger than expected. They have 57 pulsars, and the frequency at which they're seeing evidence of correlations is a frequency at which we also see evidence of correlations. And I haven't looked at it in detail, but I think that those signals are comparable to one another. So I don't think that they're different from each other. And FAST is astonishingly sensitive, right? So if you're looking at 57 pulsars, the more pulsars you get, the better you're going to do. And if you have a fantastically sensitive instrument, it's not surprising that you might see something right when you get to the edge of our band. Yeah.
So one more hand here, but I don't remember.
Hi, thank you for the great talk. What sets your upper frequency limit?
What sets our upper frequency
Yeah, I
limit?
saw like one of them went to like 26 nanoseconds or something.
Yeah, so the upper frequency limit is set roughly by white noise. So when we're dominated by detector noise as opposed to the background or something like that, that's mainly where it happens.
Thank you.
Okay, so I'm gonna run over there, the other side. Let's see questions from the other side. Thanks, James.
Hi. So you mentioned that your results outperform constraints ultralight dark matter in a way that outperforms atomic clocks. Can you elaborate on that? And what metric are you using to compare these results? And by how much?
Yeah, I'm sorry. So I've summarized that paper as best I can, but I'm not familiar with a lot of the details of all of the models that are in that paper. So I'm sorry. Yeah.
Congratulations. How does your sensitivity scale in time? 20-year baseline, how will the error bars change?
Yeah, so it's nice to get more time because if your signal is growing with frequency, as you go to lower frequencies, you're going to get more sensitive. And so, it should roughly scale with the size of the background at this point. In terms of the lowest frequency end. Sorry, I've probably not said that very well. But yeah, so your background is increasing as you go to lower frequencies. So the point is that you're going to be detecting a larger and larger signal as you go to lower and lower frequencies because the signal is inherently larger at lower frequencies. So the more data you get, the larger the signal you're going to end up getting, basically.
So the uncertainties decrease linearly in time?
Should know that. I'm sorry. I don't know if it's linear off the top of my head. I think it's square root of time, but yeah, because it's an incoherent background. But yeah.
One question from Simona, and then we'll take a question from online.
Yeah, so some of the fundamental assumptions in the parameter estimation are that it's like stationary and isotropic background. If you find evidence that means that that's no longer true, like if you get resolvable binaries or anisotropy, how much harder does that make the data analysis?
Yeah, so the data analysis is pretty mature for doing those searches because we're already doing those searches, but it is very computationally expensive to model, say, both Hellings and Downs background, a background with Hellings and Downs correlations, and say an individual supermassive black hole source, because you just have these massive matrices that you're trying to invert, in addition to subtracting off like a deterministic signal. So I would say, makes it significantly harder. Yeah.
So we have a question from the chat from Dongzi. Shannon et al. 2015 said a 2 sigma upper limit of a factor of 2.4 below this, and IP28 2016 2 sigma with a factor of 1.5 below this. What's this difference?
Yeah, so there are a few differences there. So the Shannon et al. Paper used their most sensitive pulsar to set that limit. And in this case, we're using a full array. And there are some papers that will show that you can get a bias in your upper limits if you use a subset of your pulsars to set your limits. And so that's one of the main reasons why we think that in this case, we're seeing something that's larger than that limit was. In terms of the IPTA in 2016, I think in this case, let's see, what's the right answer here? It's not surprising that you would, before you start to make a detection, you would start to set limits on the order of where the actual signal is, right? And by detection in this case, I mean for a common process. And so if you're looking for autocorrelations, before you start to see actual full evidence of these autocorrelations, your upper limits are going to start to be on the same order of what you're actually seeing. And those upper limits are also often quite prior dependent and things like this. So, yeah. I don't know if others have anything to add to that.
Further questions? Yeah, I think that's I agree with your interpretation. There's one, right at the center. No, you.
I can yell it.
Oh yeah, go ahead. Yeah.
So you showed how you're only sensitive to the gravitational waves at the pulsar at the Earth, but then how do you get redshift sensitivity, which I understand is like sensitivity to different distances? So you showed like one plot that you constrain things at one redshift and not another?
So the redshifts, there were redshifts of the binaries that are contributing to the background. So in this case, it's the redshift of the systems that are contributing to the background itself, not the redshift of the gravitational waves that we're actually measuring.
Right, so it's the distance, but how do you get distance sensitivity? I guess that's my kind of question.
Oh, well, in this case, it's going to have to do with the models that you use to build for your supermassive black hole binary population, and then your distances and your masses and things like that will be dependent upon the amplitude of the background that you have and the modeling that you've done.
Thank you.
Question here?
Yeah, thanks for the great talk. Just a question. With further data, do you think that it would be possible to constrain likely scenarios for how supermassive black holes come into existence using the data that you've collected, specifically like on the formation of supermassive black holes and models relating to that based on merger?
I don't think so. No. Yeah. No.
2 more questions back here. Sure, thanks. And then Jonah in the back.
Great talk. So I think there were like electromagnetic detections of or candidates of supermassive binary black holes. So are these pulsar timing arrays looking at like different separations of those, or is it like, is there kind of overlap?
So at the moment, I don't think that, well, it depends on what we're talking about here. So I think if we're talking about looking at like variability of light curves for AGN and things like that, then some of those could certainly be emitting in our band. At the moment, most of those candidates are things that are too far away for us to see. But people do targeted searches at some of those most promising candidates. And those searches are in progress right now, but we haven't presented results from those at this point.
Thank you, Pat. Great talk. I'm curious, it seems like the power law in frequency, the shape of the frequency spectrum is really important in distinguishing models. How well are you constraining that power law index at this point? Yeah, that's a good question. I would say reasonably well. I mean, it still depends upon the noise models that we're using, for example, and things like that. And we only have so many frequencies at this point that we're actually constraining. So I would say that this is one of the reasons why we want much longer baselines, because we're going to start to be able to constrain things at lower and lower frequencies. We're going to get more frequencies that we can see and things like that. Yeah.
Thank you. A question back there?
Hi, thank you. So kind of two halves to this. First of all, is like based upon the amount of sensitivity you've got to different frequencies, given the strain, do you know roughly how many systems you might expect to see given like the volume that you can get to? And then also based upon your actual measurements, is there any way to constrain like the number of potential binary systems that you're seeing as part of the background?
Do you mean individual binaries, or do you mean like the total number that are contributing to the background?
Yeah, the total number contributing to the background.
Yeah, so that's going to depend upon the modeling that you're doing and the models that you're building. But I think that they're in the paper that on astrophysics interpretation, there are some estimates for the number of binaries that are contributing based on the models that are built there. And that paper does a great job of going through sort of how those models are built from the ground up, and what a lot of the assumptions are that go into them, and how a gravitational wave spectrum can constrain those models. So this is one of a very
of many very useful and helpful plots for understanding those things. But yeah, I mean, over there on the right-hand side of that plot, you can see roughly an estimate of the number of binaries that are contributing and at different frequencies and at different masses and things like that.
I have another question here. Oh.
Can you say something about, you have 68 pulsars that you track. What is the observational cadence with which you go and visit each one, and for how long?
Yeah, so the observational cadence is once every couple of weeks to a month. Observation timescales are usually half an hour, yeah. One of the interesting things about Meerkat, which is the array of dishes in South Africa, is that they're looking at 80 pulsars every 2 weeks. And so they have a faster cadence, and that's something that's very useful for trying to detect continuous waves. And so that's an interesting experiment to keep an eye on.
Oh, yeah.
Hi, Pat. What a great result. So you mentioned earlier, and also this morning, we heard a little bit at the event about sort of all the different efforts that have been going on to measure this signal. And as to date, there isn't, I think, no joint constraint set. And so I was wondering if you could tell us a little bit about sort of what are the options, what are the obstacles to make a joint fit, and also what are the gains that we can hopefully get from making this?
Yeah, so, okay, that's a great question. So there was in 2022, the second data release of the IPTA and results on a gravitational wave background search for that. And in that case, they combined data sets from all of the different, from the EPTA, the NANOGrav, and the PPTA. Right now, there's a data combination effort that's going on. And at the end of that, what you'll end up with is one sort of super data set that includes, I think, of order 110 pulsars and of order 20 years of data. And once you get more pulsars, you get way more correlations that you can use to fill out that Hellings and Downs curve. And I think that the sort of the time scale and the number of pulsars that we're talking about means that we're going to improve significance, our significance estimates greatly, hopefully, once that data combination effort is done. In the meantime, there's work ongoing just taking the individual data sets and the results from those individual data sets. So plots like how we constrain the spectrum and doing comparisons between different data sets using the processed results. And that stuff is hopefully going to be done on the timescale of months, whereas the data combination effort is going to be a little bit longer. Yeah.
And I should say, because data, all this takes a really long time. Actually, the next data set has already been collected.
Yeah.
We're just waiting for the timing group to give the data to us.
Great talk. Could you explain why you expected the turnover in the lower frequency because of the contribution from the binaries, like other?
Say that again, sorry?
So you said that you expect the turnover at the lower frequency because of interaction with other astrophysical sources like clouds and stars. Can you elaborate on why you expect that?
I said that I expect the signal to be lower. Oh, like a turnover at low frequencies, for example? Yeah, so what's happening there, I think, my understanding of the astrophysics there is that if you get sort of interactions between the gas and the binary that are hardening the binary, then it moves through the frequency spectrum faster. And so you get more binaries at higher frequencies and relatively fewer at lower frequencies than you would if the binaries are hardening only due to gravitational wave emission. And so that 13/3 is assuming these binaries are only getting closer together due to gravitational wave emission, but if you have these extra gas dynamics and things like that, you're going to have to harden. And in some ways, that's something that has to happen for them to even be emitting in the pulsar timing array band at all. And so that turnover in the spectrum should happen somewhere, and hopefully it'll happen at a place that we can detect.
Thank you.
I lost. Okay.
So what's limiting adding new pulsars to the array, and what are the projections on future array sets?
Yeah, okay, so that's a great question. So we're always looking for new pulsars to add to the array. So what you want are pulsars that rotate very stably, which means that you want millisecond pulsars. And these can be difficult to find because they're often in binaries, which makes them harder to find. And their radio emission is quieter than, say, your typical run-of-the-mill pulsars that spin maybe once or a couple times a second. So they're a little bit harder to find. And then on top of that, you want to be able to observe them for a certain length of time before you add them to your data set. So the next data set, I think, will have 82 pulsars, of order 80 pulsars from NANOGrav. And there are other collaborations that have more pulsars. The nice thing about the data combination for the IPTA is that Park's pulsar timing array and Meerkat are sensitive to pulsars in the southern hemisphere, and so a lot of those are pulsars that we don't have in our data set. So yeah.
All right, let's end here by thanking Pat again. Remember, wine and cheese in the patio. If you have more questions, we'll be there. Thank you.